Okay, let's get started. So, are there any questions since last week? None? Okay. So, last lecture before spring break. Anyone ready for spring break? Absolutely. I am in that camp too. So, so if you'll bear with me for 2 more days, Monday, Wednesday, I think we'll have a good spring break. So, what did we talk about last Monday? So a whole week ago. So we were talking about meta-heuristics. So the short summary of this is we're using an algorithm to make a covering array, or hope to make one, so that the algorithm tunes its performance as it's going. So it makes some kind of analysis of how well it's doing and then adjusts accordingly along the way. So a heuristic in general is just a statistic about what's happening. So how things are going. A meta-heuristic is when you're trying to do analyses on the statistics themselves, how well you're doing, and then try to make decisions that are good depending on what happens. So we talked about this optimization formulation. Again, a good band name. So what we want to do here in general, and I guess this is really a life type thing, so it's not just for this class. We have some function that we want to optimize. So whether that's optimize a normal function or try to make a decision that's best in terms of cost, we try to optimize some kind of function in some way. So we have some function f, and we want to find an input that either maximizes or minimizes or whatever we want to do with it. So in our context, we looked at something called the deficiency, and that's the number of uncovered interactions. If that number is 0, then we got a covering array. So in this case, we want to minimize the number of uncovered interactions. But we could very well say, well, let's talk about instead the number of covered interactions and try to maximize that one. So there are multiple ways that you can phrase this. And yet there are actually more ways that you could phrase it here, but let's just stick with this. So if the deficiency is 0, we're done. Otherwise, if it's not 0, we make changes to try to make it 0. So we talked about a number of different ideas. So like, what is the neighborhood? What is a single move? Then we started to talk about hill climbing, which is the first meta-heuristic. So the idea behind hill climbing is we want to get to the top of the hill. So we take the method of steepest descent, and we just keep going in that direction until we hit the top. Okay, so we talked about this, but the problem with this idea is that we get stuck sometimes. So if there are multiple hills, for example, and if we proceed up this slope to the top, and once we get to this top, we're stuck, but there may be some better hill somewhere else. So the problem here is that it usually gets stuck. So that's why we had this little bit right here about saying or equal to. So if the deficiency is ever equal after a single move, then that means we jump to another hill and then maybe that hill's better. So that helps with the local optima, but it's still, you get stuck quite a bit because it never permits a bad move. So it may be better to, accept a bad move now and then proceed to the real summit versus I'm never going to accept a bad move ever. So hill climbing gets stuck, but it's often very quick. And if you have a domain where there is a single hill like this, hill climbing is fantastic. But in this domain, there's often more than one. Okay, so then we talked about some other ones like Great Flood, where you basically just have some kind of parameter, and as long as you're under the line, then you're okay. and so you can accept some bad moves. So like if you are going up, like the deficiency goes up, but we're still under the line, then we'll accept that move. So it does permit bad moves, but the problem is trying to choose what that threshold is. And it's absolute in that if you go over the line, you're definitely not taking it, and if you stay under the line, you're definitely taking it. So it's a hard boundary that is being chosen here. So so I'm not sure if this has actually been done, but is there a way that we can incorporate a soft boundary? So maybe if we're within 5% of the boundary, we'll do one of the two operations, either accept it or not accept it with equal probability. So I don't know what the answer is there. That might be worth looking into. Then we looked at a much better one, which is simulated annealing. And this one is really, really powerful. And in fact, it's so powerful, there are hundreds of papers on covering arrays with simulated annealing out there. So, in fact, we're reading one on Wednesday. So make sure to read it for Wednesday. Okay. And how did that one work? If the deficiency goes down, we always accept it. If the deficiency goes up, then we'll generate a random number and accept that bad move with some probability. And that probability of acceptance for a bad move goes down as we go further and further. So at the very beginning, we'll accept bad moves very frequently, but as time goes on, we'll accept bad moves less and less often. So we're kind of converging onto the summit in some sense here. Yeah, so that's what we have done. And simulated annealing actually is proven to be optimal if we run it for infinitely long, but of course we can't do that. Hopefully some of you incorporate simulated annealing into your project in some form, because it's extremely powerful for this particular domain. Any questions on the ones we've talked about so far? Yeah.
For simulated annealing, do you need to like interpret how gradually you decline? Like you have to just sort of like intuitively know? Or...
Yeah, so that's the one thing that I don't really like about this whole domain, is that you just kind of have to stumble across the ones that work. So the ones that are very effective in terms of simulated annealing, and we'll see this in the paper, is an exponential decrease. So this is the one that usually works. So basically, the function f of x is proportional to e to the minus x, where x is the number of iterations. So the number of iterations goes on, we go down with some exponential probability. And this is actually not exactly right, because sometimes there's some scaling factor in the exponent here. So if you just do a naive exponential decrease, it'll go down way too quick. So what people sometimes do is they divide x by 2 or something to make it less gradual, but still exponential decrease. But some kind of exponential is what is usually done here. Yeah. And so at the very beginning, we have to set an initial temperature, so to speak, because remember, simulated annealing is based on the annealing of metals, which is based on having the metals be at an extremely high temperature so that we can make changes to them. So the initial temperature is also something to consider. And in the paper that we're going to read for Wednesday, I think that is 4. And that has more or less been the accepted number to start out with for the initial temperature. But of course, there are some differences and pros and cons of having a different temperature. But this is the one that has been used most often. Yeah, there are also some things that can also be done. So what some people do, and if you look in the literature, this is what is also done, is at each point, we will make a move. But, yeah, so I'll just write that. So at each point, we make a move. But what is sometimes done is, instead of having one move that can be done, you alternate between two moves. So you have, let's just say, move 1 here, which might be we modify a single entry, a different kind of move that we can do, which is, actually I'll just write it. So modify 1 entry. The second one might be modify 1 column, etc. So you can have multiple moves that you can make, and at each point, we could choose one of these with some probability. So the first one, let's just say there are 2 moves. Then the first one I'll select with 50% probability, and the second one with 50% probability. And by doing that, I'm not trying to uniformly optimize with one particular move, which may get me stuck in local optima. So by having one move where it's very local, in the sense that you're only modifying a tiny portion of the array, versus the second one, which is modifying a lot more of the array and going back and forth between the two, that is actually what most people do. And the reason why people publish so much is that in this particular area is they choose one set of moves over another one, or they incorporate some other type of strategy here. But like the initial temperature and the exponential decrease, those are pretty much uniform across all of the papers published in this. The only real differences are in like the different moves that you can make, or what the with which frequency we're going to make those moves, or what the moves are. So yeah, so if you're going to incorporate simulated annealing into this, well, first off, read the paper on Wednesday, and second, have some kind of exponential decrease in high initial temperature. That's usually my recommendation. Any questions? Okay. Yeah, so I think we've talked about simulated annealing way too much. So Taboo search, this used to be really popular, but recently it hasn't been very widely used. And I would like to see it for it to have a comeback, but incorporating this, it seems to be quite difficult in terms of improving what is best known. So the basic idea is Taboo is basically a list that you keep of moves that you can't make. So let's just say that our list here is move 1, move 2, move 3, move S. And what we do is, suppose now we're going to make a move, and usually what we would do is we would just modify an entry or in a column or something. But now I'm going to do that so that I don't choose a move from this list. So the reason for doing this is that we're not going to do a similar move twice in a row, or very close to each other. So if I did a particular move like 5 moves ago, I'm not going to do it again for a long time. So I'm not going to repeat things that I've already done. And this actually has produced really good covering arrays as a result, but it hasn't been really widely used since then. Mainly because how do you actually construct the Taboo list? How long should the list be? As well as, well, if I add something to the list, when is it going to ever be taken out of the list? So if I just keep adding the moves to the list, at some point I'm going to run out of possible moves I can make. And of course, that's a bad idea. So what some people have done is, after 1,000 moves, for example, then I'll start removing things from the list. So basically I'm keeping track of the last X moves, or 1,000 moves, or whatever. So that's what's been done, but in terms of extending this idea, I'm not sure what can be done here. Maybe there is a way, and maybe some of you are smart enough to contribute something here, but this hasn't been widely as popular. Any questions about taboo search? Okay, so now the big boy. So this is one that I've recently gotten into, and there's kind of a resurgence of using this technique. It used to, there used to be experiments way long ago, several decades ago, using genetic algorithms, and what was shown at the time was that they're not very effective at all. They're just not effective. And what has recently been done within the last few years is there's kind of a resurgence of genetic algorithms. So what's the idea? So basically what we're going to do is we have a bunch of people right here, our population, and we're going to breed them. We're going to breed these individuals together. So maybe that these two are going to form an offspring, and these two are going to have another offspring. And so now we have 6 individuals, let's just say. And now I want to have the population become more quote-unquote fit as time goes on. So the parents had some amount of fitness. Maybe they were fit or they were not fit. And in choosing their offspring, or like producing their offspring, maybe they're more fit. So what we will do at a certain point is, maybe a different color. Now, after this point, we will select the 4 fittest, whatever that means, individuals to carry on their quote-unquote genes to the next generation. So maybe that this parent, and both kids are the most fit individuals. And what we'll do is now they're the 4 individuals in the population. Now we'll breed them and then carry on the next generation and just keep going, trying to keep the fittest individuals at each point. And what I mean by selecting the fittest individuals is not necessarily that, but that's the idea. We're trying to make the population as fit as possible at each step. So there are some other things that you can do, like we're going to always keep the fittest one and then some of the most fit ones and some of the least fit ones, because maybe they're carrying a gene that is really useful for fitness, but they're just not expressing it. So that's the idea behind genetic algorithms. We have a population, we're going to breed them, and then we're going to carry their genes to the next generation, and then repeat. The next generation breeds, and then we produce more offspring and keep going. So that's what we're going to do here. So I'm only going to describe one way to work with genetic algorithms, and if you want, I can talk about a recent preprint of mine where I use genetic algorithms in a completely different way. So what we're going to do here is we're just going to talk about the one row at a time method. And so now we got to produce a row, and we want the row to be good. So we're going to keep a population of candidate rows. So we're going to have a row here, row here, row here, row here. So a bunch of rows that could be placed there. And at the very beginning, we're just going to have the rows be completely random. So no thought into it. And what I'm going to call the fitness is how good an individual is. So maybe it's like how fast can you run a mile or whatever, some kind of fitness measurement for each of the individuals. Each individual has some fitness. And the fitness of a row, in our case, is the number of interactions that we're going to cover for the first time in this row. And how do we form the next generation? How do we breed these rows together? So The two common operations are these ones. I guess not operations, but family of operations, because there are so many different choices that you can make with these two. And so mutation is, of course, when two parents breed to produce offspring, they're not going to get exactly the genes from their parents. It's going to be some combination of them as well as external factors. So they're not going to be uniformly like their parents, but there's going to be some modification. So mutation is we're going to make a small change to the candidate row. So maybe you change one entry and not think about it, just change one entry and that's it. So that's pretty simple. So you just change one row, no thought into it. So crossover is the more controversial in this area. So crossover is how do you actually breed the two rows together? And I'm not going to say that there's a particular way of doing this, but I'll highlight one way, which is something called one-point crossover. So what does that mean? And the way I'm going to describe it here, there's only one point, but you can have multiple points. This is not like this is the only way to do it. There are multiple ways to do this. So let's say that we have individual 1 here, which is a row. And then let's say here's the second individual, another candidate row. So how does one-point crossover work? What you're going to do is you're going to split the rows. You're going to draw a line between the rows. So something like this. And how crossover works is you're going to pick one of the pieces from one of the parents and the other piece from the other parent. So maybe, for example, I select this portion from the first parent and this portion from the second parent. So we're getting some of the quote-unquote genes from one parent and the genes of the other parent. Any questions on how that works? Yeah.
How do you usually determine how big to make the splits between those two option rows?
Good question. If you know the answer, please tell me. So there isn't a way that is like this is the best way. What people usually do is just pick the point at random. So have no thought into it. And that usually performs well in the general sense, but doesn't really perform well here. So many experiments on my part and other people's parts is that crossover usually does not perform well in this domain for the one row at a time method. So it may perform well in a different context, but not here. And how do I show that? I show that by, oh, go ahead.
So for this method, this crossover means that you're taking assignments from halfway in a row and assignments to halfway in another row and putting them together.
Yeah, so I take two candidate rows, I split them at the same point, pick one piece from one parent, pick the other piece from the other parent, and stick them together. And then that's the new individual. And then, so then now I have the original parents as well as the offspring. And then what I do is I just select which are the best fit individuals at each point. So what do I mean by crossover doesn't perform well? When I form the children, it usually is the case that, so it's usually the case that the fitness doesn't increase very often. So it's usually that the fitness either stays the same or goes down. And the reason for that is that the individuals after a certain number of generations are very highly fit. And because of that, any small change to the individual's representation, the row, is going to make a big change. So when I'm going to take a piece from one individual and one piece from another one, that's a huge change compared to just making one little modification. So that's the reason why in this particular context, crossover doesn't work well. In a different context, which I will talk about at the end, it actually does perform well. But so this is the reason probably why genetic algorithms in this domain did not catch on, because crossover just never performed well. Other questions about GAs? Okay, so one of the things that genetic algorithms in other contexts have shown is that they're even more powerful than simulated annealing, but the downside of them is that they're really expensive in terms of how much computation you have to do. Because if I make one small change to the row, I got to redo the whole computation, potentially. So, and I'm going to be doing these crossover of these individuals, and I have no guarantee that I'm going to improve on the individuals that I have. So it's just a way of trying to get fit individuals, not necessarily a way to get to the optimum necessarily. It's trying to get to the optimum. Okay, so what can I say about this? Yeah, so there are some ways of choosing the individuals. So another point of research is how do we select individuals for the next generation? And that's actually something that hasn't been really investigated in this domain. And I would love to see an answer to this. So by what we usually do and what has been done is we just choose a candidate based on how fit it is. So if I have a list of individuals right here, and let's say that as I go up this list, the fitness goes up. So the very best individuals at the top, then the next best, and the next best, and then the worst individual at the bottom. So how does it work here? Well, I'm going to select the top candidate here with the highest probability. And then I'll select the next one on the list with slightly less probability. So it's proportional to your fitness. And there's a reason why it's called proportional fitness selection. So we select individuals based on their fitness, but we're still doing it randomly. So it's not like we're just picking the top 10 individuals and keeping them forever, because that will actually lead to local optima too. Yeah?
Wouldn't fitness of rows depend on what rows you selected before?
Yes. Yes. So that's also a huge problem too. For the first row, it doesn't matter because you're always going to have the same fitness, but rows after that, it could be anything. So yeah, so the row order matters. And this is actually one of the other reasons why this is not a good algorithm, because now it depends on the previous rows. If you did the entire array at once, this would actually succeed a lot more often. And in my experiments has shown to be much more successful. But it's much more computationally intensive now, because now you have to have the whole array at once. What else has been done? So what sometimes people do is, if we look at this fitness chart again, maybe we select the top 3 individuals always, regardless of what happens, and then a random sample of the other ones. So maybe that some individuals will always breed or should breed a lot more often than if we just selected the top individuals. Because we want to have the genes that may or may not be expressed in other individuals to propagate up to the higher fit ones. So that's sometimes been done, but it hasn't been shown to give really good results. So let me show you, or at least tell you about what I've recently done. So let me put a new page. Okay, so what did I do and how did I show that genetic algorithms are good in this domain? So let's just say that we want a covering array of higher index, lambda. So we want to make a covering array with high redundancy. So what do? Instead of having a genetic algorithm make the array itself, what we're going to have is a set of algorithms that we can choose. So maybe we have algorithm 1, so maybe that might be the density algorithm. Algorithm 2 may be the random one, algorithm 3, etc. So we have a set of algorithms that we can choose at each point. And so here's what we're going to do. So the individual in this case is a choice of algorithms with corresponding index lambda 1, lambda 2, etc. So algorithm 1, let's just say we picked algorithm 1. Then the index 1 here means once algorithm 1 is done, then I'm going to have a covering array of index lambda 1. And then lambda 2 means once I finish with the first one, I apply algorithm 2 now, and I get an array of index lambda 2. And so at the very end, after I've applied all the algorithms, I'll get one of index lambda. So the individual here is a choice of the algorithms with the index that we want. And we will have the individuals just initially be random, just like before. And mutation is what you might expect. We're going to change one of the algorithms for maybe another one. There are some other ones that I did too, but that's the basic idea. And how does crossover work? Well, it's one-point crossover. So you have your algorithm list for one individual, algorithm list for the other one, draw a line, pick one from each of the two parents, and then put them together. And that has actually been shown to be really effective. And there were vast improvements that I was able to show based off of this. So I don't want to toot my horn too much, but the point here is that genetic algorithms, even if it's not particularly effective in one domain, it might be effective in another one, and it has been shown here. So any questions on genetic algorithms in totality? Yeah.
And changing the domain to be more meta, like having the genetic algorithm just kind of like sort through and pick individual algorithms to make arrays. What would, given that you have to make like minor changes to them in order to continue to add more like covering, I guess, row options or array options, what changes would you make?
So the downside, I guess, of my method is that every single one of my algorithms I chose was deterministic. There's no randomness. And the reason for that is that once I finish the first algorithm, because it's deterministic, it will always be the same. So what I can do with the individual is I can save computation time by just storing the result after the first algorithm. And so incorporating randomness into this is something that I would want to do. But making small changes could be different parameters to the algorithms themselves. I have not looked into that yet. So what I have is basically just off-the-shelf algorithms, and I just apply them in the natural way. For higher index, I needed to generalize them, but it's basically off-the-shelf here. Yeah, that is something to look into. And if any of you want to do something similar genetic algorithms wise, then I can help you with that.
So is an individual a set of algorithms for each of the lambdas?
Yeah, so the individual is, here's algorithm 1 paired with an index. Algorithm 2 paired with an index, yeah.
So how do you create the CE?
Yeah, so this is basically what happens. So I'm going to break this up into a number of what I call stages. So at stage 1, we're going to apply algorithm 1 to obtain a CA with lambda 1 as the index. Then in stage 2, we're going to take the CA that we got from the first stage and feed it in to the algorithm for the second stage. And then here, after algorithm 2 is done, we're going to obtain a CA with lambda 2 as the index. So where lambda 2 is bigger than lambda 1. So maybe if lambda 1 is equal to 2, lambda 2 is equal to 3, etc. Then after the first stage, I'm going to have a covering array of index 2. And then I'm going to feed that into the second algorithm I chose. Maybe it's the same one. And at the end of that algorithm, I'm going to get a covering array with index 3. And then if my target is 5, for example, then I'm going to apply more and more algorithms until I get to the target index I want. So in terms of like mutation and crossover, I'm not only modifying the algorithms, but I'm modifying the index too. And there are some profound results that I was able to find, mainly that the best thing that you can do is to have every algorithm have index 1. So the first algorithm is index 1, then 1, then 1, then 1, then 1, then 1, every time. And it's not like there's some better choices if you want better results and some choices if you want things to run fast. It's uniformly index 1 on everything. And there's some explanations for why that's the case. But that's basically what's happening here, or what I did. You're basically trying to make the algorithm in stages rather than just all at once. And the advantage of this is for the second stage, it has less work to do because you already have every interaction covered twice. So you only need to cover them one more time instead of having to cover them all 3 times. And based on how algorithm 1 does, algorithm 2 might have even less work to do because some interactions already may be covered 3 times. So, yeah. Any other questions about genetic algorithms, though? Okay. So the very last one is something called particle swarm. This is, there has been some work recently on this, and as far as I remember, there's only one paper recently on this, but it was actually a very good paper, so I guess there is some activity here. But if you want to incorporate this into your project, I would highly recommend doing this also. So the basic idea is kind of like genetic algorithms in that we still have a population of sorts, but here we're going to model them like particles instead of individuals in a population. So maybe let's just say that this is our population of particles right here, and we have a certain target right here. So that's the target. And we want to direct the particles toward the target, if possible. So what we are going to do is we're going to maintain several things. Well, each of the particles knows which direction it needs to go in order to hit the target. So each particle knows its direction that it needs to go. But the problem is, if they just go uniformly toward the target, there may be a bunch of obstacles in the way. So they may not be able to go uniformly toward the target. So what do you do here? Well, you have every particle make a move, and then you try to assess what has happened. So maybe at some point, some individual got stuck at an obstacle. So you keep track of how well did the entire swarm, as it's called, do. So did they all uniformly move the same distance? Or did some of them get stuck and then we have to reassess what we need to do? So we pick a speed and a direction to move for each particle. So you have to decide how fast you're going to move toward the target as well as what direction to go. And how do you determine what the speed is? It's based on how fast you went recently. So maybe if you're going really fast now, should you go just as fast as you did before, or should you go a lot slower, or it depends on various factors. Should you change direction? Should you keep going in the same direction or deviate slightly? So another one that might be is, well, you may, for a particular particle, you may have chosen a bunch of different directions that in previous iterations. Well, you may want to weight the ones that go toward the target the best. So maybe for this individual right here, let's just say that we've tried all of the directions within this, what do you call that? Like the sector of the circle. So we tried all of these different directions in this sector. Well, maybe the one that the arrow is, that's the one that's pointing toward the target. So that one should be weighted more than the other ones because it's better in that it's pointing toward the target. But maybe the other ones might be effective, so you want to include them too. You want to weight them accordingly. And you may also want to look at how well did the entire population do. So it's not like each of these particles is working in isolation. They're working as a group, as a particle swarm. So you have to keep track as well of how well did the population do. So is it that some particle did really well and most of the other ones didn't, or did everyone do well? You have to keep track of that sort of thing. And the problem here is, what is the speed and the direction? Because we're dealing with a discrete object here. It's not continuous. So if I adjust my speed, I gotta make the change to the speed in discrete steps because we're dealing with a discrete object. So that's what the challenge is. I would highly recommend reading the one paper about this. I can give you a reference if you're interested. But any questions on particle swarm? Yeah.
Could you describe a little more how the moves themselves would be discrete?
The thing is, I don't remember. The move. So is it like how the moves work, or?
Yeah, how the moves work.
So the move would be in this particular context. It would be, let's just say that we have a row that we want to add to an array, and then I make a change, and then here is, so maybe like it was a 0 before, and now it's a 1. So the red's the modified array. So what we could say is, are we moving toward the target? So what the direction is, did the deficiency go up? So if the number of interactions left uncovered went up, then we're moving away from the target, because the target is always going toward 0 deficiency. So if the deficiency went up, then we're moving away from the target. But if it went down, we're moving toward the target.
So just, right, not necessarily random, but just some sort of step that increases coverage.
Yeah. So, but the problem is that if you think about it, well, you're either moving toward the target or moving away. So you can think of this particle swarm as you're moving on a one-dimensional line, which might not be very effective. So the challenge here is, how do you formulate this in a way so that you get more dimensions out of it? So you get more directions to possibly search in.
Okay.
Yeah, so that's what the challenge here is, and I don't know any off the top of my head. Any questions? So remember, we're reading a paper for Wednesday on simulated annealing, and I'll see you then. Make sure to sign in the sign-in sheet if you haven't yet.